exercise 3.7. So in this one we have to provide group tables for these two given groups. So the first one has 3 elements, so the table is this. You can write, I mean, when you are writing the solution, you have to properly write all the things, right? So you can write the following is the group table of Z3 or C3. Those things I am not going to write. I will just simply show the table. So the elements in C3 or Z3 are these. Additive groups, the binary operation in this one, in the first one is addition modulo 3, which is, let us also recall what that is. According to that operation, for example, when you add 1 and 2, it's not actually 3, but rather the remainder you obtain when you divide that 3 by 3. So the thing that by which you are dividing the modulus in this case is 3. Okay, so 0 plus anything of course is going to give you that thing itself, which because it is a non-negative integer, whether it is 0 or 1 or 2, it is a non-negative integer less than 3. So that itself will be the remainder when you divide that by 3. So that is why 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. And because our binary operation is commutative, it does not matter in which order you operate on two elements. So 1 plus 0 is also 1, 2 plus 0 is 2. 1 plus 1 is 2. When you divide 2 by 3, the remainder is 2 itself. So the result of this operation is 2. Now here 1 plus 2 is 3, and when you divide 3 by 3, the remainder is 0, so you get 0. Just like that, 2 plus 1 is also 0, and 2 plus 2 is 4, and when you divide 4 by 3, the remainder is 1. So this is the group table for the first one. In the second one, it's the Cartesian product of Z3 and Z2. This one has 3 elements, this one has 2 elements, so the Cartesian product will have 6 elements. Accordingly, we have to see how many rows and columns there will be in this table. Okay, ideally the elements should be written like this. I mean, because the set is the Cartesian product of two sets, so each element will be an ordered pair, and it will be an ordered pair. For example, 1, 2. This is an element in this set. But because if we write like this, we would need much more space than we have in these cells. So instead, we are going to write it more compactly as 1, 2. This may create confusion. I mean, if you don't say anything and just simply continue to write like that, it will create confusion. But for the sake of saving space, and because we have less space in these cells, I mean, you can imagine if we write like this, if we write the actual ordered pairs, we need a much larger table. I can cram things here itself, but it will look messy. When we finish writing the whole table down, it will look messy. So instead, it's better to write like this. And in fact, let us just mention this, since this is not something standard. You should not do this in a solution. I am doing it here for our own convenience. In the above table, the symbol AB denotes the ordered pair A, B belonging to our Cartesian product. So in Z3 we have 3 elements. These are the 3 elements. In Z2 we have 2 elements. So these are the elements according to our new notation in this Cartesian product. 0, 0, 0, 1. The second number in each such symbol is coming from Z2, which is either 0 or 1. And the first number is either 0 or 1 or 2. So 1, 0, 1, 1, then 2, 0, 2, 1, like that. 0, 0. It's not necessary that you should maintain this same order along the columns, and the same order in which you have written the rows. In this first row you have to maintain that same order. That is not necessary, but it is just for the sake of symmetry we write like that. So 0, 0, then comes 0, 1, 1, 0, 1, 1, 2, 0, 2, 1. And what is the binary operation in this product? It is just simply this. If you have 2 elements, say you have A, B here, and you have, say, another element C, D. Then, according to the operation that we have in this product, it is just A plus C, B plus D, where this first calculation, the first coordinate calculation, is done in the group Z3. So this addition is addition modulo 3. You have to ordinarily add the integers A and C and then divide this sum by 3. Whatever remainder you get, that remainder is the answer here. Similarly, this one is addition modulo 2. So here whatever sum you have by adding these two things up, you have to then divide it by 2. The remainder is your answer. So now first of all, this 0 0 will have no effect on these elements, just like this 0. 0 1 1 0 1 1 2 0 2 1, then 0 1 1 0 1 1 2 0 2 1. Okay, now we carefully do the, fill out the rest of these cells. 0 1 plus 0 1 is the first coordinate is 0, so 0 plus 0 is 0. 1 plus 1 is actually 2, but because we are doing the calculation in Z2 or Z2, that 2 is 0 because we are dividing by 2, so the remainder is 0. Just like that, 0 1 plus 1 0, 0 plus 1 is 1, 1 plus 0 is 1. Okay, then 0 1 plus 1 1, 0 plus 1 is 1, 1 plus 1 is again 2, and in Z2 2 is 0. 0 plus 2 is 2, 1 plus 0 is 1, and finally 0 plus 2 is 2, 1 plus 1 is again 2, and that is 0. Now note that if you now go column wise, you will get just the same things, same pairs of summands in the opposite order. What I am trying to say here is that in this row, whatever you have written, that is 0 1 plus 0 1, 0 1 plus 1 0, you see 0 1 plus 1 0 is this cell. If you look at this cell, that is 1 0 plus 0 1, the order is changed. Here you have 0 1 plus 1 1, in this cell you have 1 1 plus 0 1, and we know that the binary operation in this group also, like the previous one, is commutative, so the order does not matter. So whatever you have written in this row, the exact same things will now appear along this column. So 1 0 plus 0 1 is again 1 1, which of course you can find also by directly calculating, but just I am saying a simple thing about group tables of abelian groups. It's the fact that if you look at the main diagonal cells, that will contain some elements. In the upper diagonal part, you calculate all the things. The lower diagonal parts, that is the cells below the leading diagonal, they are just, if you look at the main diagonal cells like this, then whatever you have on this side, this is the mirror image. So 1 1, 1 0, 2 1, 2 0. This will speed up the calculation. But keep in mind, this is only when the group is abelian. You know for sure that the operation is commutative. Then only you can have like this. Now, for the sake of confirming whatever we have written is actually true, let's for once directly calculate these column entries. 1 0 plus 0 1 is of course 1 1. 1 1 plus 0 1 is 1 plus 0 is 1, 1 plus 1 is 2, but 2 is 0, yes. 2 0 plus 0 1, 2 plus 0 is 2, 0 plus 1 is 1, yes. 2 1 plus 0 1, 2 plus 0 is 2, 1 plus 1 is 2, but that is 0. So the rest of the cells we can now fill out like this. Okay. The next is 1 0 plus 1 0. So this is 2 0. Keep in mind that the first number can be 2. The moment you have 2, that is not necessarily, in fact that is not 0. In the second numbers only, whenever you encounter 2, in its place you have to write the remainder when you divide by 2. That's why it becomes 0. Okay, next 1 0 plus 1 1. 1 plus 1 is 2 and 0 plus 1 is 1. Okay, now next this one 1 0 plus 2 0. 1 plus 2 is 3, but that first calculation is in Z3. So in Z3, 3 is 0 because you are dividing by 3, so the remainder is 0, and 0 plus 0 is of course 0. Then finally 1 plus 2 like that is 0, and 0 plus 1 is 1. So now you have these column entries 2 1 0 0 0 1, 2 1 0 0 0 1. Then 1 1 plus 1 1 is actually 2 2, but that second 2 will become 0. So 2 0. 1 1 plus 2 0. 1 plus 2 is 3, 3 is 0. 1 plus 0 is 1. 1 1 plus 2 1. 1 plus 2 is again 0. 1 plus 1 is 2, so this is 0. So now we have got these column entries 0 1 0 0, and then 2 0 plus 2 0. 2 plus 2 is 4. In Z3, 4 is 1, and 0 plus 0 of course is 0. 2 plus 2 like before is 1, and 0 plus 1 is 1. So we now have 1 1. And finally 2 plus 2 is again 4. 4 means in Z3 1, and 1 plus 1 is 2, so this is 0. So this is the composition table. It is also called known as composition table sometimes. We compose two elements and the results have been shown here. You can see that in these tables the first row and first column have been reserved for the group elements themselves, and the actual calculation is in the rest of the table. So depending on how many elements the group has, you can guess the number of rows and number of columns. Here in this second one, for example, there are 6 elements in the group, right? So besides this first row, you need 6 rows 1 2 3 4 5 6. Like that, besides this first column, you need 6 columns 1 2 3 4 5 6. Just like that here also. So you need one more 1 2 3 4 1 2 3 4, because its order is 3. Order is the number of elements in a group. So that is the solution. The solution actually ends here, but of course these extra things are there. So let us next see. The next one is also similar. 3 8. Give group tables for the following groups. This time we have U12 and S3. Okay, so first of all, we need to know what the elements in U12 are. You know from the definition of U12 that U12 consists of all positive integers less than 12 and relatively prime to 12, and there are 4 such integers. 1, 2 and 3 are not relatively prime to 12, 4 is also not relatively prime to 12, 5, 6 is not, 7, 8 and 9 are not, 10 is also not, 11. Okay, so these are the elements in this group. So we do need one more row and one more column here. We can modify this table itself. One more row and one more column. One, 5, 7, 11. 1, 5, 7, 11. Okay. Now the operation in U12 is multiplication modulo 12. So just like there we had in C3, we had addition modulo 3. We had to add two numbers and then divide their sum by 3. The remainder is our answer. This time we have to multiply the two numbers and divide the product by 12, and the remainder will be our answer. So because 1 will not have any effect on these things under multiplication. So we have 1, 5, 7. I mean, when you multiply anything or any one of these numbers by 1, you get the number itself, and the number is a positive integer less than 12. So when you divide that sum by 12, the number itself is the remainder. Like that, this operation is also like the other things, other two operations we have seen so far, commutative. So 1, 5, 7, 12, 1, 5, 7, oh sorry, I mean 11, not 12. Okay, now next, 5 times 5 is 25. Now when you divide 25 by 12, the remainder is 1, so 1 is the answer. 5 times 7 is 35. Here the remainder is 11. Then 5 times 11 is 55, and here the remainder turns out to be 7. And because again, just like before, 11, 7. You verify these calculations, okay, that the remainder actually is 7. 7 times 7 is 49. Okay, 4 times 12 is 48, plus 1 is 49, so this is 1. 7 times 11 is 77, which you divide by 12, you will see that the remainder is 5. So this one is also 5 because the operation is commutative. And finally, 11 times 11 is 121. 121 is 12 times 10 plus 1. So here the remainder is 1 when we divide by 12. So this is the group table for U12. Now the next one, S3. This one, however, is non-Abelian. We have already seen this before. So here the group table is not going to be, you won't be able to quickly calculate the group table like this by calculating the upper portion of the leading diagonal cells. And we have to in fact name the elements also, because in S3 we know the elements are the permutations on 3 symbols. So let us first name the elements. Well, but before we go to this second one, there is something else that can be said about this U12. It's not, just to know how many elements there are in U12, it's not necessary to actually find the elements. There is a formula for that in number theory, which is your familiar Euler phi function, phi of 12. How this formula works is this. If you know the prime factorization of the given integer, for this one say we know 2 and 3 are the distinct prime factors of 12. So what you do, phi of 12 will calculate this number, the number of integers, positive integers less than 12 and relatively prime to 12. You okay, I won't have space for this. Let me show it there itself. What you do, you calculate this thing, that is, you multiply the given integer by these other numbers, where you can see what we have done. For this 2 we have this factor, for this 3 we have this factor. So what will this be? 12 times 1 over 2 times 2 over 3. This is 4, and there are 4 elements. So like that you can calculate the order of this group, the number of elements. Okay, now next, in S3 these are the permutations. Let we have already seen this notation, so we can use that to say which permutation is being denoted by what symbol. It does not matter which one you call what. What matters is depending on what symbol you are assigning to these permutations, ultimately your group table should be correct. 1 2 3 1 3 2. I have the thing calculated here, so I'm trying to maintain that same thing, because if something goes wrong I can look at this. 1 2 3 1 3 2 2 1 3. There are better and more compact notations for these things which will come afterwards. Sigma 3 is 2 3 1. Three one two, 3 2 1. These are of course not standard notations. I have just decided to name them like this. Okay. Now instead of trying to fit things here, let me do the thing here. And plus we need to calculate the products in this case more carefully, because it's not like the previous groups, it's slightly more complicated. Let me create some space here also for our calculations. Oh, there are 6 elements, 5 sigmas and 1 identity. This is going to be identity, which we already know. So that means there should be 7 rows and 7 columns. Okay, the cells have not been of equal size, but we will carefully write things. Okay. Okay, so let us first write the elements. E, sigma 1, sigma 2, 3, 4, 5, 6. Oh, okay. We need one more, no? Sigma, okay, what the hell have I done? I think I have taken one row less and one column more. Okay, so unnecessarily I have taken one extra column. Because of this increased space, we can make the cells a bit larger, but let's not just do those things. Now row count is okay. Column has been taken one extra because we have up to this only. Oh, so that's just it. So now you can see that, right? So E is going to be our identity element. If you ask why, that is because E is the identity permutation. It does not change anything. So whether you, for example, calculate E sigma 1 or sigma 1 E, that is not going to affect sigma 1 in any way. So you are going to end up with sigma 1 itself. So that's why this part at least is like the tables we have seen before. Sigma 4, sigma 5. And although this group is non-Abelian, the operation is not commutative, but E itself commutes with every element. I mean, EA is equal to AE is equal to A according to the third axiom in the definition of a group. So E already commutes with all elements. So for this column at least you can in fact write like before: sigma 1, sigma 2, sigma 3, sigma 4 and sigma 5. Okay, now comes the time for these careful calculations. First comes sigma 1 square, that is sigma 1, sigma 1. Now if you look at these things, these permutations, for the sake of clarity, let's just write all the things for this one and see what we get. 1, 3, 2. 1, 2, 3. 1, 3, 2. Recalling that our calculation starts from the right side, although in this case it would not matter, but still 1 goes to 1, 1 goes to 1, so 1 goes to 1, 2 goes to 3, 3 goes to 2, so 2 to 2, 3 to 2, 2 to 3, so 3 to 3. So we get the identity. Okay, then next sigma 1, sigma 2. So we can continue our calculations like this, one at a time. So sigma 1 is like before 1, 3, 2, and sigma 2 is 2, 1, 3. 2, 1, 3. Oh, so this is not as difficult to write as I previously thought. 1 to 2, 2 to 3. So 1 to 3. 2 to 1, 1 to 1. So 2 to 1. 3 to 3, 3 to 2. So 3 to 2. Which one is this? 3, 1, 2. Sigma 4. So this is sigma 4. Then sigma 1, sigma 3. Sigma 1 is this one, sigma 3 is 2, 3, 1. 2, 3, 1. Okay. 1 to 2, 2 to 3. 1 to 3. 2 to 3, 3 to 2. 2 to 2. So 3 will go to 1. 3 to 1, 1 to 1. Yes. 3 to 1. 3 to 1 is sigma 5. Oh, I had to change these things also, no? Sigma 1, sigma 2 I have done just now. Sigma 1, sigma 3 right now we have done. 2, 3, 1, 2, 3, 1, and this is sigma 5. Have I confused myself here in calculating this one, sigma 1, sigma 2? Let me just see. 1 to 2, 2 to 3, 1 to 3, okay. 2 to 1, 1 to 1, 2 to 1, 1 to 3, 2 to 1, 1 to 3 to, no, it's okay. Okay, next sigma 1, sigma 4. 3, 1, 1 to 3, 3 to 2, 1 to 2, 2 to 1, 1 to 1, 2 to 1. So this will be 3, 3 to 2, 2 to 3, 3 to 3, 2, 1, 3. 2, 1, 3 is sigma 2. And then this is going to be sigma 3, sigma 1, sigma 5 next. So for the fifth one is 3, 2, 1. 1 to 3, 3 to 2, 1 to 2, 2 to 2, 2 to 3, 2 to 3, so this one will be 1, 3 to 1, 1 to 1, yes, 2, 3, 1, 2, 3, 1 is sigma 3, yes. You may have noticed one thing, that after calculating this first two, I am saying that the other one should be that, the remaining one. Why? That is because both these are permutations, that is one-to-one onto functions. So their composition also has to be a permutation. So once we have got 2 and 3, the only other choice for this one is 1. So it's in fact not necessary to really calculate the third one. The third one you can be assured that it will be the remaining one. So that will slightly speed up the thing. And now don't make the mistake of writing sigma 4, 5, 2 and 3. They may not be the same thing. So now the order will change. Now sigma 2, sigma 1. Sigma 2, sigma 1. So sigma 1 is 1, 3, 2, 1, 3, 2. And sigma 2 is 2, 1, 3. Okay, so here we go again. 1 to 1, 1 to 2, 1 to 2, 2 to 3, 3 to 3, 2 to 3, so this one will be 1, 2, 3, 1, 2, 3, 1 is 3. Note that sigma 1, sigma 2 is sigma 4, but sigma 2, sigma 1 is sigma 3. They are not the same thing. Okay, next sigma 2, sigma 2, of course. So this one need not change. This one will be 2, 1, 3. Okay, 1 to 2, 2 to 1, 1 to 1, 2 to 1, 1 to 2, 2 to 2, so this one will be 3. So this is E. Then sigma 2, sigma 3, 2, 3, 1, 1 to 2, 2 to 1, 1 to 1, 2 to 3, 3 to 3, 2 to 3, so this one will be 2, 1, 3, 2, sigma 1. Sigma 2, sigma 3, so this is sigma 1. Next, sigma 2, sigma 4, 3, 1, 2, 1 to 3, 3 to 3, 1 to 3, 2 to 1, 1 to 2, 2 to 2, so this one will be 1, 3 to 1. 3 to 1 is sigma 5. And this one will be sigma 4. Just like there is a remaining one thing here, in this table itself also there is a remaining one thing. I will say why that is so. In the previous row also, while calculating this, I said that this is sigma 3 even before calculating, which was the one that did not appear here, and that is always going to be the case. So what I am saying here is that this is going to be sigma 4 because that has not appeared here. Sigma 2, sigma 5. Let's see. Sigma 5, 3, 2, 1. 1 to 3, 3 to 3, 1 to 3, 2 to 2, 2 to 1, 2 to 1, so that means this will be 2, 3, 1 to sigma 4 C. Okay, next I will explain the reason afterwards. Okay, next sigma 3, sigma 1. So sigma 3 is 2, 3, 1. 2, 3, 1, and sigma 1 is 1, 3, 2. 1 to 1, 1 to 2, 1 to 2, 2 to 3, 3 to 1, 2 to 1. So this is going to be 3, 2, 1, 3, sigma 2. Next sigma 3, sigma 2, 2, 1, 3. 1 to 2, 2 to 3, 1 to 3, 2 to 1, 1 to 2, 2 to 2, so this one will be 1, 3 to 1, sigma 5. Then sigma 3, sigma 3. So 2, 3, 1, 2, 3, 1. 1 to 2, 2 to 3, 1 to 3, 2 to 3, 3 to 1, 2 to 1, so this is 2, 3, 1, 2. Okay, I am doing the calculations fairly fast, so let me just stop for a moment and see more carefully whether I have actually done it correctly. 1 to 2, 2 to 3, 1 to 3. 2 to 3, 3 to 1, 2 to 1, so that means the other one is 2, 3, 1, 2, 3, 1, 2 is sigma 4, 4, then sigma 3, sigma 4, 3, 1, 2, 1 to 3, 3 to 1, 1 to 1, 2 to 1, 1 to 2, 2 to 2, so the other one is 3. So this is E. Sigma 3, sigma 4 is E. So what has not appeared? Sigma 1. So this will be sigma 1 in the next one. Sigma 5, 3 to 1. 1 to 3, 3 to 1, 1 to 1, 2 to 2, 2 to 3, 2 to 3, so this will be 2, 1, 3, 2, yeah, 1, 3, 2, sigma 1. Two more rows are left, so now comes sigma 4. Let us first put that 3, 3, 1, 2. 3, 1, 2. First sigma 1. Actually first we have E, but that calculation is already over. Sigma 1 is 1, 3, 2. 1, 1, 1, 3, 1, 3. there is one more small thing about these calculations. You see, we are using the same template for calculation for these calculations by erasing the things, the previous things, and then using it again for the new thing. While doing so, you see that these numbers already were there in the previous calculation. Now if you don't erase them at once and keep them, say you first change the first number, then you change the second number. At that time, while calculating the second number, you erased it and you write the new answer, and then you change this one. This this will create a situation where it's very easy to make mistakes. It's much more convenient to wipe these things completely and then start the calculation, because if at any stage you forget where you are, then you won't know whether your value that you see here is the previous one or the new one. Okay, so now 1113 is 13, 2332 is 2, so this is 1, 321 is sigma 5, 4141 is sigma 5, then 42, 213, 1 to 2, 2 to 1, 1 to 1, 2 to 1, 1 to 3, 2 to 3, and so this one will be 2, 132, 132 is sigma 1, then sigma 4, sigma 3, 231, 1 to 2, 2 to 1, 1 to 1, 2 to 3, 3 to 2, 2 to 2, so that means this will be 3, and this is E. So this is E. You can see one thing, that along the leading diagonal, these E's have appeared in the first 3 rows and first 3 columns. But it's not necessary that that will continue to happen. You can see that sigma 3 is not E, it is sigma 4. Sigma 3 is E. So don't just arbitrarily see some such pattern and think that that is always going to happen. Next, sigma 4, 312, 312, 1332, 1332, 211323, so this is 1, 231, 231 is sigma 3. So what has not appeared? Sigma 2, so this is going to be sigma 2. The next one, 5 is 321, 133212, 222121, so this is 3, 213, 213, sigma 2. There is one more thing. You may have noticed that, you may or may not have noticed that I have used 3 rows to write these elements, where in the first row, the second rows of these permutation symbols start with 1. Here they start with 2, here they have started with 3. this also has a purpose. The purpose is that the moment you finish this calculation, looking at this first number, you can, it becomes somewhat convenient to find what this permutation is here, depending on what number you have here. If this is 2, you search here in the second row. If this is 1, you search here. Okay, so sigma 4 calculations are over. Next, sigma 5. Sigma 5, sigma 1. Am I already running out of ink? We will see. Sigma 5 is 3, 2, 1. Sigma 1 is 1, 3, 2. One, 3, 1, 3. 2, 3, 3, 1, 2, 1. So this is 2. 3, 1, 2. 3, 1, 2 is sigma 4. Next, 2, 2, 1, 3. 1, 2, 2, 2, 1, 2. 2, 1, 1, 3, 2, 3. So this is 1. 2, 3, 1. 2, 3, 1 is sigma 3. Next, 3. 2, 3, 1. 2, 3, 1. 1, 2, 1, 2, 2, 2, 1, 2. 2, 3, 3, 1, 2, 1. So this is 3. 2, 1, 3. 2, 1, 3 is sigma 2. 2 more. Sigma 5, sigma 4. 3, 1, 2. 1, 3, 3, 1, 1, 1. 2, 1, 1, 3, 2, 3. So this is 2. 1, 3, 2. Sigma 1. Okay. And this one will be E, what has not appeared. Sigma 5. 3, 2, 1. 1, 3, 3, 1, 1, 1. 2, 2, 2, 2, 2, 2. So this will be 3. And in fact, you can actually see 3, 1, 1, 3 is 3, 3. So this is E. Okay. Now, how am I able to say that in the last stages of these calculations along each row, the last one is the remaining one? That is because if it is not the remaining one, for example, in this row, or for the sake of simplicity, in this row, say this is not E, then this is not E means what? It will be one of these. Just for the sake of argument, assume that this entry is sigma 4, say. So that means what? Sigma 5 is sigma 4, but at the same time sigma 5 sigma 1 is also sigma 4. Right. And now see, this is a group. Okay, we know that this is a group, so sigma 5 has an inverse. Now if these two elements are equal, this one and this one, then multiplying them by the inverse of sigma 5 will also give us equal elements now gives the fact that in a group the binary operation is associative. So this thing is this. And this by the definition of inverses E. And this by the property of identity element. This one, the first one is sigma 5 and the second one is sigma 1, and this is a contradiction. This is not true. Sigma 5 and sigma 1 are two different elements. So that is why we will have the remaining element, and what we are saying here ultimately means this. When you calculate the elements in a composition table or a group table like this, what happens is that you will get new elements. There is no repetition along a row. E sigma 1, sigma 2, 3, 4, 5. 1 E 4, 5, 2, 3. At no, along a row you will never get repeated elements. If you get, then you will get a contradiction like this, or if you suppose that there is such repetition, you end up with a contradiction like this. So there cannot be any repetition. The same thing also happens along the columns. So these group tables have this nice property that every element in the group appears in exactly one row and exactly one. No, what I am trying to say is this. Every element in the group will appear in every row and will also appear in every column, but exactly once. Yeah, that is the thing. Every element, I am again repeating, you take any element of the group, that element will appear in every row and every column, but exactly once. For example, if you take this element sigma 2, it has appeared in the first row here, sigma 2, but only once. Here also sigma 2, but only once. Here also sigma 2, but only once. Sigma 2, sigma 2, sigma 2. If you look at these columns in which these sigma 2's have appeared, in the first row it has appeared here. In the second row it has appeared here. In the third row it has appeared here. In the fourth row here. In the fifth row here. And in the sixth row here. And these are along different columns. So this appearance in different columns correspond to non-repetition along a row, and appearing in different rows correspond to non-repetition along a column. Okay, so anyway, this is the composition table or group table for S3. There is a name for this property. It's called there are two such properties, cancellation loss. We will see those things. Now next, So group composition tables or group tables have that property that magic squares that each number appears in exactly, I mean in each row exactly once and in each column exactly once. The next one, yeah, now we really need ink. Yeah, it will take some time to come properly. 3, 9. I keep writing without stopping. Show that the product of these two groups G and H, G cross H, is abelian if and only if G and H are abelian. And by the way, if you find these things somewhat confusing at this stage, just forget about them. Okay, we were supposed to find the group table, we have done that, and that's just it. We will see these things again when the time comes. But now we have two groups and their Cartesian product is abelian if and only if both of them are abelian. First, assume G and H are abelian. We now have to prove that the Cartesian product is abelian. Let G1, so we take two elements here in the product and show that they commute. Belong to G cross H. Then I should perhaps not say G cross H, but I should rather say G Cartesian product H, because cross really means cross product of two vectors. Then G1 and G2 belong to G and H1 and H2 belong to H. Since G and H are abelian, we have G1 G2 equal to G2 G1, and like that H1 H2 equal to H2 H1. So this is equal to no matter how much we write in whiteboards, blackboards are the best. Blackboards and chalk pieces. I don't have good blackboards here where I live. Otherwise, I would have bought that itself. G2, H2, G1, H1. You should understand that these products are being calculated in the respective groups. So whatever binary operation we have in these groups, they are there. For example, in between G1 and G2 we have the binary operation that we have in G. Like that, we have the operation in H here. We are using that to calculate this product. But because it is difficult and cumbersome to come up with different symbols for each binary operation, then writing them here in between, it will make things quite messy. So that is why we have the multiplicative notation in which we do not write anything and understand that the operation that is there between two elements is the one in the group from where the elements are coming. That's just it. So just like that, between these two ordered pairs, we have the binary operation that has been defined in this on this Cartesian product. So that's just it. These two elements commute. It does not, the order does not matter. You get the same answer. Hence, this is Abelian. Conversely, assume that the Cartesian product is Abelian. We now have to prove that both the groups are Abelian. Let us first show that G is Abelian. Let A and B belong to G. Then A, E and B, E belong to G cross H, where E is the identity element in H. Since G cross H is Abelian, we have AB, E equal to A, E, P, E. Now the fact that we have assumed this to be Abelian allows us to write this product by changing the order. And that now, again, by the definition of the binary operation of this Cartesian product is equal to BA, E. So these two ordered pairs are equal, hence the corresponding coordinates or entries should be equal. The second entries are of course the same, but the first entries are the same, from which we get the fact that A and B commute in G. Hence G is Abelian. Similarly, one can show that H is abelian. And this part I want you to do just as a practice. So that's the solution. Next, let G be a group containing at most 3 elements. Show that G is abelian. At most 3 elements. Show that G is abelian. So that means G can have either exactly 1 element or 2 elements or 3 elements. So we will look at these 3 cases separately. First, assume that G has just 1 element. Then that single element is of course the identity element, and the G in this case is obviously in a trivial manner abelian, because the only product you can now think of is EE. That's just it. So we don't write that thing. In this case, G is trivially abelian. Next, assume that G has 2 elements. Let G consist of E and A, where you understand that E is the identity. Then EE, there is no point considering a product where both the factors are the same. You for abelianness, you want AB to be equal to BA. So if both A and B are equal, then AB and BA are the same thing trivially. So the only thing that you should see here are the products EA and AE. But both of them, by the very fact that E is the identity element, are the same, and that same thing is A itself. So G is abelian. This is also easy but not as trivial as this one. So the complexity keeps on increasing as the number of elements increases. Next, let G have exactly 3 elements. And let the elements be E, A and B. E is the identity element, A and B are some distinct elements different from the identity. We don't really know what they are or how they behave. The only thing we know is that they are distinct and they are also both different from E. That much only we know. Okay. So to show that this G is abelian, the only thing that really we need to show is that AB is equal to BA. In this case, however, their equality cannot be seen directly like this, because none of them is equal to the identity. So we have to argue, we have to have some sort of argument to justify that they are equal. Note that AB and BA both belong to G, because G is closed under its binary operation, so both these products will belong to G. Whatever they ultimately turn out to be, they after all are in G. Okay, in fact let us write like this. Suppose AP is equal to A. So this, supposing this is in a sense like supposing that elements get repeated in the group table in that calculation, because now we are going to do something which is similar to that calculation. Then let me write this thing here. A inverse AB is equal to A inverse A. See, A has an inverse which may either be A or B or E. Actually it will not be E, but just for the sake of argument, right now what we need is the fact that A has an inverse which is coming from G. It is there somewhere. That is guaranteed by the fact that G is a group. Then use the associative law that is also there in the group. So at every step, whatever you are doing should have a justification. And this is E. This is E. B is equal to E, which is a contradiction because B is different from E. So our supposition is wrong. AB cannot be equal to A. So supposition is wrong, i.e. AB is not equal to A. Similarly, one can show that AB is also not equal to B. If you assume AB to be equal to B, you can do a similar calculation, this time not with A inverse but with B inverse, which will give you the erroneous conclusion that A is equal to identity, which is not true. So AB is also not equal to B. So AB can neither be A nor B, but AB must be in G. So the only possibility is that AB has to be equal to E. Thus, we must have AB equal to E. And whatever we have done, all these things with AB can also be done with BA. Similarly, BA is also equal to E, but then AB is equal to BA. Hence, G is abelian. So we cannot have a non-abelian group which has 3 elements. In fact, this result is true not just for 3, 2 or 1 elements, but for 4 and 5 elements also. Groups which have at most 5 elements are all abelian. Non-abelian groups start from 6 elements. And one such group, of course, is our S3, which has 6 elements. So this completes the solution. Next. Explain whether why neither, I said whether, there is no such word. Explain why neither of the following is a group. So two systems are given to us. The set of positive rational numbers under division and number 2, the set of rational numbers q greater than or equal to 1 under multiplication. Solution. The operation of division is not associative on the set of positive rational numbers. And this is the reason. 1 divided by, in order to show that this is, I mean, if you want, you can use this slash also. In order to show that this is a binary operation, I am writing like this. Now this is what actually? 1 divided by 2 divided by 3. This is equal to 3 divided by 2. It's a rational number that is not equal to 1 divided by 6. And if you look carefully, 1 divided by 6 is this. Okay, so it's not associative, so how can the system be a group? The second one, the set of rational numbers under multiplication. The element 2 in the given set, because 2 is a rational number greater than or equal to 1, in fact strictly greater than 1. This has no inverse. Now inverse in the set under multiplication. And why is that so? Because under multiplication its inverse is 1 over 2, and 1 over 2 is not in the given set. 1 over 2 is not greater than or equal to 1. So because of these reasons, the systems, given systems, are none of them is a group. Next, is either of the following a group under addition? Again, two systems are given, the set of even integers. And number 2, the set of odd integers. Number 1, it is a group. Why? Because the operation is addition, right? The sum of 2 even integers is even, so that means it again belongs to the set. So the set of it, so the given set is closed under addition. And addition of integers is an associative operation. So in particular, addition of even integers is also an associative operation. The additive identity 0 is even, and for an even integer, its negative is also an even integer. And in fact, this is not just a group, it's an Abelian group, because addition of integers is commutative also. A plus b is equal to b plus a. Minus a is also an even integer. The second one is not a group. It is not a group because it is not even in the first property itself, it fails. It is not even closed. If you add two odd integers, it's not an odd integer, it is even. Or we can write like this: this is not odd. Next, I am unsure of how much time has elapsed. It's still recording. Perhaps I should keep a watch with me. So let's just go. I want to complete this set of exercises. Let's see how many we can do. Let G be the set of complex numbers for which the sum of the squares of the real and imaginary parts is 1. Is G a group under multiplication? Yes, it is a group. And in fact, pictorially, if you think of the complex plane in which you represent each complex number as a point, then this set is your unit circle centered at the origin and having radius 1. Let a plus bi and c plus di belong to G. And the set, of course, is, in all these cases where we are saying that the system is a group, in all of them the corresponding sets, the underlying sets are non-empty. Okay, we are not explicitly mentioning that because the cases we have come across so far, that is obvious. Here also it's a non-empty set. So we have taken two elements, then a square plus b square is 1 and c square plus d square is also 1 because they are coming from G. Now what happens if we take their product? Now a plus bi times c plus di, if you do the calculation, you will see it becomes ac minus bd plus ad plus bc times I. And now what happens if we take the sum of the squares of the real and imaginary part of this product? Then it becomes a square c square plus b square d square minus 2acbd plus, if we expand this one, a square d square plus b square c square plus 2 ad bc. These two things cancel each other, and whatever remains, you can see that is equal to a square plus b square times c square plus d square. A square c square plus a square d square plus b square c square that we have here plus b square d square. And both of these things are equal to 1. So this is 1. So here also we are getting 1. So the product of these two complex numbers also belongs to G. That means G is closed under multiplication. Multiplication of complex numbers is associative. It's a fact which one can prove also, but it is something we already know from elementary theory of complex numbers. Then the multiplicative identity, the complex number 1 is in G. Why? Because 1 is 1 plus I0 and 1 square plus 0 square is 1. Next, what about inverses? Say this has been considered to be an element in G. What about its inverse, multiplicative inverse? The multiplicative inverse is this. Okay, by the way, what is the guarantee that this is a non-zero complex number? Because if it is not non-zero complex number, then its multiplicative inverse will not exist. Ordinary multiplicative inverse. It is non-zero because a square plus b square is 1. It is coming from G. No, so this will make sure that a and b cannot be simultaneously 0, because otherwise this left hand side would be 0. So this identity tells us that it is a non-zero complex number. So that is why we can write like this in the first place. Now you know how to express this in the standard form. A minus IB, A plus IB times A minus IB. So this is equal to A minus IB divided by A square plus B square, and A square plus B square for us is 1. So this luckily is just A minus IB. Now since this A minus IB also belongs to G, to see why, you take the sum of the squares of the real and imaginary parts of this inverse, that will be A square plus minus B whole square, that will also be 1. So G is a group under multiplication, and in fact it's an abelian group. Complex number multiplication is commutative. Right. Next, so that's just it. Yeah, that's it. We don't have anything else. 314. Let G be the following subset of C15. Namely 3, 6, 9, 12. Show that G is a group under multiplication in C15. That means the binary operation is multiplication modulo 15. Find the identity. In the course of showing that this is a group, we will also do these things. Find the identity and the inverse of each group element. So what we will do here, we will form a group table for this, and in that table you will have to write the formal answer, the formal solution, of which the group table will be a part. So in the group table itself we will identify the identity and the inverse of each element, and we won't say anything more. We won't say means I won't say anything more. You please complete the solution from this table. Three, 6, 9, 12, 3, 6, 9, 12. So you have to keep in mind that the binary operation is multiplication modulo 15. So you have to first multiply and then you divide the product by 15. The remainder will be your answer. For example, 3 times 3 is 9. 3 times 6 is 18. So when you divide 18 by 15, the remainder is 3. So this is 3. Like that, if you calculate the other products, you will see that you get this. Let's not waste time on doing the actual calculations here. Instead, I copy this from what I have already done. 3, 6, 9, 12, 12, 9, 6, 3, and 6, 12, 9, 3. Here also, before we say something else, let me digress a little bit, and let us recall that thing again. Each element appears in each row and each column exactly once. That thing continues to be true in any group table. Okay, so you can see that. Okay, but by the way, how is it a group? First of all, our operation has not led us outside the set. Whatever products we are calculating, the answer is always in this set. So that means this set is closed under multiplication modulo 15. Multiplication modulo 15 is known to be an associative operation. So that is why it is associative. You can see that 6 behaves as an identity element. You multiply anything with 6, you get that thing itself. 6 times 3 is 3, 6 times 6 is 6, 9, 12. Like that, if you change the order, if you see on this side, 3 times 6 is 3, 3, 6, 9, 12. So 6 is our identity. So that means 3 and 12 are inverses of each other, because 3 times 12 is 6, 12 times 3 is 6. We are getting the identity. The inverse of the identity is of course itself. 6 times 6 is 6, and the inverse of 9 also happens to be itself. 9 times 9 is 6. So identity is there. Each element has an inverse, so it is a group. Okay, so you write all those things and complete the solution. Next, let P be a prime and G is the set whose elements look like this: a divided by p to the power n, where a is any integer and n is a natural number, a positive integer. Is G a group under addition? Yes, it is. Let me show you. Here also I am not going to write a formal solution. I will just show you the actual thing and then you write the formal solution based on that. What do we need? We need to verify that the four axioms are satisfied. So first of all our set is obviously non-empty. Now if we take any two elements from this set, how would they look? A divided by p to the power n and b divided by p to the power m, where a and b are integers and n and m are natural numbers, positive integers. Then if you add them, you get this. This numerator, whatever it is ultimately an integer, because a, b, p, m, n, these are all integers, right? And in the denominator we again have a power of p, where the exponent is a sum of two natural numbers, so which is again a natural number. So this belongs to G. So that means G is closed under addition. And the addition that we have is actually the addition of rational numbers, because after all these are some special types of rational numbers, but after all rational numbers. So addition of rational numbers is associative. So associativity is also there. What about identity? The identity under addition is the rational number 0, which also belongs to G, because for example 0 can be written like this: 0 divided by p to the power 1. So this belongs to G, and for any element in G, its inverse is its negative, which also belongs to G, because you can take the minus sign with the numerator. So a is an integer, minus a is also an integer. So this again belongs to G. So yes, this is a group. And finally, we have this one. Let G be the set of all matrices. Matrices of this form. One A B 0 1 C 0 0 1. The author is using round brackets. I prefer square brackets. There is no difference actually. With both are in use. with A, B and C integers. I hope you can see this. This is 1. Below the main diagonal, all the entries are 0. Above the main diagonal, we have other entries which are integers. Show that G is a group under matrix multiplication. Is G abelian? So this exercise is straightforward. You have to again show that the 4 axioms are satisfied, and the set G is of course non-empty, and the binary operation is matrix multiplication. Now here I will do even less. I will only show that G is actually not abelian. Showing that G is a group, as I am leaving that to you entirely. Take 2 such matrices, take their product. You will see that the product is the gain of that form. So G is closed. Matrix multiplication is a known associative operation. So that associativity is also there. The 3 by 3 identity matrix, which is this matrix where A, B and C are 0, is also of this form, so it belongs to G, and that is the identity element under matrix multiplication. Then comes the question of inverses. For inverses, what you do, you note that the determinant of this matrix, whatever A, B and C may be, is non-zero. You actually calculate the determinant, so its ordinary inverse will exist. You go through the procedure to find that inverse that you already know. You will see that ultimately the inverse also turns out to be of this form, so it belongs to G. So that way you can prove that G is a group. Now it is not abelian, and that follows from these 2 matrices which do not commute. In general, arbitrary matrices rarely commute, so it was not particularly difficult to find these 2 matrices. I just simply took 2 matrices and that's it. They do not commute. 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1. If I calculate this, you will see that you get this. Whereas if you change the order, one minus 1, 1, 0, 1, 2, 0, 0, 1, then you get 1, 0, 4, 0, 1, 3, 0, 0, 1. So the 2 matrices differ in their first row, third column entries. So they are not equal, and that's why the group is not abelian. It's a non-abelian group. And this completes this set of exercises. In the next video, we will then go to the next set of exercises. And these Lee videos appear along with the Galilean videos on Saturdays alternatively. So this Saturday, for example, we have seen Lie exercises. Next Saturday we will again see Galilean exercises, and then again Lie. It goes like that. And tomorrow, of course, we have our analysis, where we will first settle that second rule of exponent. We will first prove that, and then we will go to the theory of infinite series and their convergence. So that will be all today in this video. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address, which is there in the description. So that's just it. This is me, Lucifer, signing off from a mathematical room. See you tomorrow. Have a nice night.